My name is Maxim Andreev. I am a software developer. I write in several languages like C, C++, and so on. You can find me on Twitter, on GitHub, and on Telegram by handle cdump or by this avatar. So today I'm going to talk to you about my tool, EVMole. We'll start about function selectors. I describe the need for extraction selector tools. I will take a look into existing solutions, talk about benchmarks, and then we will dig into EVMole internals. So what is EVMole? This is a library which extracts function selectors and arguments from EVM bytecode, even for unverified contracts. It has implementation in 3 languages. It's in JavaScript, in Rust, and Python, so you can use it from your favorite language. It has a clean code with 0 dependencies, external dependencies, and the main part that it's faster and more accurate than other existing tools. So, what is selector? Here's the simple Solidity code for like a simple token with one public function transfer and one storage variable balance of. If we compile this contract with Solidity compile and ask to produce binary runtime, we will get this hex code, which is basically bytes encoded in hex. It's Ethereum opcodes. And if we ask about ABI of this contract, so we run solc with -- ABI flag, then we get JSON, which describes the ABI of this contract. So you can see we have a transfer function, it's not payable, and it accepts 2 inputs and produce 1 output. And the input types is address and unsigned integer. If you ever use Etherscan and see verified contract, you can see that there are 2 tabs, right? Read contract and write contract, where you can interact with deployed contract. It's using this JSON ABI to produce this page. But if you see unverified contract on Etherscan, all you can see is just bytecode. What do I mean by interacting with contract? How can we interact with contract? All the things we can do is call contract and pass some call data. To call the function of the contract, we need to encode this call into call data. I can use cast tool from the Foundry suite here to call function balance of with which accepts address with this address, and you can see this long hex string. And the first 4 bytes of this string is the function selector, and the other part are encoded arguments. Here it's only 1 argument. So to get the function selector, we need to apply Kesak hash code to the signature of this function, which is balance of. You can read more about it on the soliditylang.org ABI spec. Why do we need tools for extraction of function selector for unverified contracts? Why I develop another one tool? At first, just for fun, it was interesting for me to dig into EVM internals to understand how it works internally, how I can outperform existing solutions. The second usage of this kind of tools is security auditing, because if a malicious actor deploy a contract, of course, he will not upload source code to the Etherscan. So if you want to understand what these contracts do, you need to decompile it, or you can use tools like only extract function selectors. And the third interesting point is to finding bugs. You can see the screenshot of the Twitter thread which I post. I find out that for some contract which is verified on the Etherscan, I thought that it lacks kill function. It is ABI and the source code. So it was very interesting, because if I saw a verified contract on Etherscan and I'm auditor, I read the all source code, okay, it has 3 functions, it's totally safe, and then some function like don't exist in this source code on verified contracts, it can lead to some dangerous situation. So I take Etherscan and they fix the bug. So tools like mine can find bug even on such a big project like Etherscan. So what are existing tools for extracting function selectors? The first one is ABI. It's written in TypeScript by Shadow and JavaScript. and other exist like EVMole and EVMhound, which are written in Rust, or you can use the DAO decompiler. But what's wrong with them? We don't know how accurate are them. We don't know which one is the best, how to choose which one to use. We don't know. And that's the first problem which I try to solve. So for that, I wrote benchmark suite. I download some verified contracts from GitHub and split it to two datasets. The first dataset is top 1K largest contracts by the size, because I thought if the contract size is large, probably it has a lot of functions, so a lot of non-trivial logic, and so on. And the second dataset is just random top 50K random contracts. As I said, it was verified contracts, so I was able to download a verified API from Etherscan, and this is our ground truth. Here we ensure that Etherscan provides correct API. So you can download it with the script in repository and get this JSON API. So the next step is to write some tools which can process datasets which I received from the previous step and output one JSON file for each dataset. As you can see, for selectors, it's like the key in the dictionary is the contract address, and the values is the array of function selectors. And for arguments, it's the same, but the key is function selectors, and the value is string of the function arguments. So I write some scripts to produce output in this form for all existing tools, like WhatsApp provider. As you can see, it's just as simple like read dir, and for every file, apply WhatsApp select from bytecode. I packed it in a Docker file, and I repeat it for every existing tool, like WhatsApp, EVMDolores, EVMhound, and so on. And I write this magic make file. It's very big. I don't expect you to read it here. It uses a lot of makefile tricks, but finally I was able to run make etherscan.arguments/largest1k. So if I want to add one more dataset or add one more provider, it was just easy as to add to the first line of the makefile one new element. So here the main thing that's now we are able to make easy and reproducible benchmark results for every existing solution. So how we want to benchmark? What is benchmark? The first of benchmark is time of execution, but the second, the more important part, is the output. For example, for function selectors, let's say we say that Etherscan is the ground truth, so this is for selectors is the true, and some tool outputs these three selectors. So here we can see that we have three errors, but two different kinds of errors. Two false negative errors, two selectors which exist in the Etherscan output in our ground truth, but lacks in some tool output. And one false positive which exists in some tool, but it shouldn't exist there because it's not exist in the ground truth. So I wrote another script which compare results from ground truth and the results from selectors, and it shows the errors, and now we can see the results of benchmarking all existing solutions. As you can see here, the less is better. So we have three data sets. The first one is largest 1K contracts, random 50K contracts, and Viper compile contracts. And you can see we don't see a lot of zeros. We want to see zero errors, but it's not. For existing solutions, we have some zeros for my solution for EVMole, and for some other data sets, if EVMole is not zero errors, it's much smaller, like 1 error versus 33 errors versus 700 errors. And talking about time of the execution, you can see that EVMole performs even faster, especially Rust implementation, like it can, for example, for largest 1K, it took only 0.7 seconds, and for EVMole count takes 0.2 seconds, but EVMole it's take 700 seconds. And the same thing about function arguments. Not all solutions can extract function arguments. So I compare EVMole errors with my solution, and you can see 32% of errors in EVMole and only 15% of errors in my solution. And for random 50K, it's only 5% of errors for my solution, and I was unable to run EVMole errors on this big data set because it has errors. I reported to the author, and probably he will fix it soon. So now let's talk about why and how EVMole works so fast and so accurate. As you know, every contract which is deployed on Ethereum or any other EVM-compatible chain executed on the EVM virtual machine. It's a quite simple virtual machine with stack, memory, and problem counter, and so on. So if we call to the contract, like I showed you before, we encode call into call data, and then we have this long call data string, and when the execution of the contract starts, we need to extract function selectors just to take first 4 bytes to understand which function user wants to call. And then if the function has arguments, we need to extract the arguments. To get the first arguments, we need to extract 32 bytes starting from the offset 4. So it's expressed in pseudo Python, and if we express in the EVM opcodes, so usually it's like push some value to the stack, call data-load opcode, and then shift right to 28 bytes to get the first 4 bytes. So first, which I did, I take a look into Solidity compiler, C++ implementation, and find the append internal selector function, which has a lot of good comments, how it works, how Solidity compilers decide how to generate code to extract function, to understand which function the user wants to call. It's different for different versions, like this is for the latest version, this is for some previous version, and you know we have not everything contract deployed is compatible with the latest version, for obvious reason, like USDT compiled with older version. But the first approach was just to find the common thing, and the common thing is to take first 4 bytes and just compare it with known selectors of this contract. So it can be expressed in this pseudocode like this. If the selector is this, call this function. If the selector is that, call that function. And the interesting part here is how we decide if the selector is some constant. So usually it's just if we expect selectors already on the stack, then we can push this constant, call equal opcode, and execute conditional jump based on that. I try to write selector extractor based on this approach, like to find all push opcodes and then equal opcodes, but it performs very bad, like a lot of errors. So something wrong with this approach. And wrong is one thing of the wrong. Even this simple compression is can be implemented in different ways by a compiler, by applying optimization, by a compiler of different version of different language like Viper and Solidity. It can be equal opcode, it can be subtraction opcode, it could be XOR opcode, or even for the older version of the Viper compiler, it for some reason use the memory. It can be implemented using just stack, which is faster and costs less gas, but for some reason they use memory. So we can use a simple approach like finding all sequences of codes, so we need to do something different. And the different way which my library implements is to make some custom virtual machine. And the main part of this virtual machine is class element. So all code here will be in Python, but as you can remember, my library has Rust and JavaScript implementation, so you can read this code in other languages on the GitHub. So class element is basically the labeled bytes. It's bytes with some label, let's say string. So the stack implemented with this element is just a list or array of these elements, a list of labeled bytes. And virtual machine can be implemented just, it has stack, it has memory, it has whole data. So then when we execute a specific opcode, so we read from the contract bytecode, the first code, and then we have the switch, like if it's call value, the amount of the Ethereum sent with this call, then we can push 0 to the stack. Let's say that message value is always equal to 0. If we want call.load, we execute call.load and label it with call data. So now on the stack we have something which was loaded from the call data. And you can see I return this the gas cost of this opcode and some other additional info. So, and to extract the all selectors of the contract using this approach, I need just to create an instance of virtual machine, pass contract bytecode to it, and pass call data as labeled data or some random data with the label call data. And then I execute step by step all the opcodes in the contract. Of course, I'm tracking the gas usage, because if we overstep the limit, we need to break. And then, for example, if we shift right something with the label call data, and the result of this shift is equal to the first 4 bytes of the call data, then we put the label signature to the result. And after that, if we execute equal opcode to some element with the label signature, then probably we find a selector, a function selector, so we need to append it to the final result. And the interesting part, Solidity compiler generate binary tree. If you have a lot of selectors, it's optimization to find the function selector faster with less gas, so we can find LT and GT less than and greater than opcodes. And on this point, I just deep clone virtual machine, just like fork. So I want to go to the left branch of this if, to the right branch of this if, to collect all possible function selectors. And if we can trace the execution of the contract, so at first we push 0. After that, we execute call data load opcode, and you can see on the third line that now we have this AABBCCDD on the stack with label call data. After that, again, push some constant, shift right, and after shift right, we have result on the stack with the label signature. And after that, we have signature, we have GT, so it's binary tree. We need to take left and the right branch of this if, and after that, we will find equal opcode of the signature, and we will put the signature to the results. Arguments extraction is basically the same. I am tracking call.load calls with offset greater than 4, because first 4 bytes is this function signature. And after that, all I need is just to deduct argument types. So usually for Solidity and Viper compiled contracts, there's AND operator after call.load with some constant bit sets. If it bit sets with 000 FFF, then probably it's unsigned integer of specific length. If it's FFF 000, then probably it's bytes of specific bit length. So the 4 points of EVMole to success: label data, control gas usage, because the function selector and the argument type extraction performs at the early stage of execution of the contract, and we don't want to go deeper into the contracts. Fork on GT and LT with gas left divided by 2, because we want to handle all possible situations, but only in terms of the selectors, so we don't fork on any GT or LT. And do not implement 100% of opcodes, because we don't expect call opcode or KESAC opcode in this part of the contract. It's early stage. and you don't need KESAC opcode to extract a function selector or to deduct its type. Usage of my library is quite simple. Like, you can use it from JavaScript. It has 2 public functions from Rust, from Python, or even from cast selectors from the Foundry. Foundry uses Rust version of my library. You can use online demo because it has JavaScript implementation. I wrote some simple UI for it. And the plans for the next, I'm trying to do storage layout extraction. One tool exists for this. It's EVM large storage on EVM.storage, but my quick benchmark shows that my approach can outperform this in terms of accuracy. So probably it will be the theme for the next talk. So thank you for your time. You can visit it here. You can ask questions. You have 4 minutes.
It's quite impressive. I was wondering if, have you thought on creating a UI in which is similar to verified EtherScan contracts, but without the verification, but you can actually interact with it. So you can have the view functions in one side and be able to see how things are, and also connect your wallet and interact with the functions of an unverified contract.
Okay, thank you for the question. I know the similar project exists. The author of the What's ABI implements some project, I don't remember the name, but the idea is the same, to extract the ABI from an unverified contract and to call it. And What's ABI after, we talked with him, and probably he will integrate my library to his What's ABI to doing this. So solution exists and you can build your own solution. It's not the part of the library. You can build it on top of it.